Alright, today we're going to be looking at balancing a redox reaction under acidic conditions. Now, the question below, that's this question over here, is actually going to be acting as a guide for us, because I'll be giving you like the step-by-step procedure. So I'm actually going to be using these questions to actually help your visualization of the processes occurring, and later on we'll actually be solving some other questions. So now the question is, write a balanced equation for the redox reaction between acidified potassium tetrahydromanganate manganate 7, KMnO4, and iron 2 tetrahydrogen sulfate 6, FeSO4. Now this is the equation for the reaction. Now this equation, if you can look at it, is not yet balanced. So I'm actually going to be showing the step-by-step procedures in balancing this equation. So now let's just start. Now, the first thing that I actually need to do is to write your oxidizing and your reducing agent in each case and deduce what the product should be. Now, the oxidizing agent in this case, as you all could guess, was manganate ion. Now, because manganate ion actually loses its oxygen as it becomes manganese, it actually loses oxygen. This is the manganate ion actually loses oxygen to become manganese. So we can also use other definitions for reduction to actually deduce what happens to the manganate ion. So now the manganate ion had an oxidation number of +7 here if you want to calculate it, and now the oxidation number changes to +2. Now from +7 to +2, that's a decrease in oxidation number. So at the end of the day, manganate ion is set to undergo reduction. Now the reducing agent in this case is iron 2 ion. Now iron 2 ion got oxidized to iron 3 ion. That is from +2 to +3. Now this is oxidation because oxidation is defined as the increase in the oxidation number of a substance. So iron 2 ion actually got oxidized to iron 3 ion. So iron 2 ion is the reducing agent. Manganate ion is actually the oxidizing agent. So now the next thing that you actually have to do is to balance the two half equations for reduction and oxidation by balancing the atoms, the charges, and the charges of each equation. Now this is done by adding the appropriate coefficient in front of each ion. Now for the case or for the example that we actually have here, if we can look at now this half equation, if you just can look at it, we don't really need to balance anything because the stoichiometric coefficient in front of the manganate ion and the manganese 2 ion is actually 1,1, and that of the ion is actually still 1,1. So we don't really need to be balancing any ion, but we are not done. It doesn't mean that we won't balance other things. So now, because we're balancing this reaction under acidic conditions, we have to add hydrogen ion to the left hand side and water or H2O to the right hand side of the reaction respectively. So now, because of that rule that I just told you, we have to add hydrogen ion to the left hand side and water to the right hand side of the reaction. We just have to do that because we're balancing this reaction under acidic condition. And if you also think of it, this manganate ion has four oxygen atoms. Now how are we going to balance that oxygen atoms if we don't actually balance the other charges? So that's the reason why, those are the two major reasons why we actually add hydrogen ion and water to actually balance it, because hydrogen ion and water, they're already present in that reaction. If you can think of it, acidified KMnO4, hydrogen ion is present there and is always balancing. This is a redox reaction, or this is a reaction that occurs in the presence of water. Water is always acting as the solvent, or most times water acts as the solvent. So we actually balance this with water and hydrogen ion. So now the solution of MnO4 we're given is acidic, so we actually have to add hydrogen ion to the left hand side and water to the right hand side. Now on doing that, we end up with this. So now the next thing that we actually need to do is actually to balance the hydrogen ion and the water present. So if you can see, there are four oxygen atoms present on the manganate ion. So how do we balance it? We add four in front of the water in order to balance the oxygen atom, and that, now on adding the 4, we've ended up like not balancing the hydrogen ion, so we just have to balance it. So this is just like 4 times 2, 8. So we just add 8 in front of the hydrogen ion, and at the end of the day, if you can look at the reaction closely, you find out that it is balanced. Now we've all balanced the stoichiometric coefficient and every single thing. That's the water, the hydrogen ion, the manganate ion, and the manganese 2 ion. But we've not balanced the charges. The charges aren't balanced. So the next step that we're actually going to be doing is to be balancing the charges. So now, okay, before we actually go into balancing charges, let's look at the oxidation half equation. Now, the oxidation half equation, we don't really need to balance anything, as you can see. That is Fe2 plus to Fe3 plus. We don't really need to add water to this or hydrogen ion to the other because it's just balanced on its own. What is just needed to balance here is just the charges. The ions are balanced, so we just need to balance the charges. So now that's the next step. We add the correct number of electrons to help cancel out the charges. Now there's this trick that I've found out that for oxidation we end up adding electrons to the right hand side, and for reduction we add electrons to the left hand side. This always works, but it's not really basically how the that's just basically what the principle is. It's just like a rule guiding it. But if you forget the rule, you can still actually decode it just by looking at it. So for oxidation, we add electrons to the right hand side. For reduction, we add electrons to the left hand side. Now, if you can now look at the charge, let's look at the reduction half equation. Now look at the total charge. Now, manganese iron has a charge or a resultant charge of -1, and hydrogen has a charge of +8 because there are 8 hydrogen atoms present, so 8 hydrogen ions present, so it has a charge of +8. So the resultant charge on the left hand side is going to be +7. Now that's on the right hand side. Water has a charge of 0 because water is a stable compound and all stable compounds have a charge of 0. And manganese iron has a charge of +2. So at the end of the day, we end up having a resultant charge of +2. Now, if you can see, the charges are unbalanced. So what do we need to do in order to balance this charge? Now, if you want to take the rule, for example, remember the rule, we are meant to add electrons to the left-hand side for a reduction equation. But if you don't want to take the rule, you can just simply use mathematics and just decode it. Now, +5, electron is always a negative charge, so electron is always minus. So now, what must you take away from +7 in order to get +2? Must take away 5 electrons. And on doing that, you add 5 electrons to the left hand side. If you take the rule, you still get the same thing. So when you add 5 electrons to the left hand side, your resultant charge end up becoming +7 +2, and that will end up giving us your resultant charge will end up becoming +7 - 5, and that will end up giving us +2 as our electron number. Now for the oxidation half equation, now the same thing we actually do, Fe2 plus to Fe3 plus. Now the resultant charge here is actually +2 because there's only iron 2 ion present, and iron 2 ion have a resultant charge of +2, while the resultant charge on the right hand side is just +3. So what must you take away? Because if you want to take the rule, we add electrons to the right hand side, but if you don't take the rule, what must you take away from +3 in order to get +2? You must take away 1 electron. So we add an electron here because electron is a negative charge. So on adding an electron here, we end up with +2 as a resultant charge here and +2 as also the resultant charge here. And at the end of the day, we've ended up balancing the charges present on the ions. So now we've ended up with the reduction half equation to be this equation that we have above, and we've ended up with the oxidation half equation. This is the reduction half equation, and this is the oxidation half equation. Let's call the reduction half equation equation 1, and the oxidation half equation equation 2, because we're still going to do something to them. So now the next step, that's step 4, we cross multiply equation 1 and equation 2. That is multiply equation 1 by 1 and equation 2 by 2. Now the reason why we're doing this is that we're multiplying the two equations by the stoichiometric coefficients in front of the electrons. So now we multiply equation 1 by 1, that is by the stoichiometric coefficient in front of equation 2 in front of the oxidation half equation, and we multiply the equation 2 by the stoichiometric coefficient of the equation 1 electron, that is -5. Now the reason why we're doing this is just so that we can cancel the electrons as a whole, because we cannot cancel the electrons. If we choose to cancel electrons here, at the end of the day we end up having a resultant electron of 4e-, and we don't really want electrons to be present in these reactions. So what do? We multiply this by 5, and at the end of the day we're able to cancel out electrons freely. So that's the reason why we do that. So now on doing that to the oxidation half equation, we end up to the reduction half equation, we end up with this, because anything multiplied by 1 is that same thing. But for the oxidation half equation, we end up with this. So now we are able to cancel out our electrons. So that's the next step by actually taking into consideration. Now, or before we do that, we just combine the two equations. Now, the next step that we actually take into consideration is actually to combine equation 3 and 4 to form a full equation. That means we combine equation 3 and equation 4 together, and we just combine them to actually form a full equation. Now, combining them, we end up with this for the left hand side and this for the right hand side. So this is just a full equation. Now, after we're done combining the two equations, we can cancel out the electrons. Now, as you can see, I've already slashed them out, but I've slashed them out again. Now we can slash out this electron and this electron. Now you see the reason why we had to cross multiply the two electron, like the two equations, by the stoichiometric coefficients of the electrons. Now we're able to do that. We're able to cancel out the electrons, and finally we end up with this equation. Now, what's the secret about all of this equation is just that if you want to actually calculate the charges on the left hand side and on the right hand side, you see that they're actually the same. The charge on manganese ion is -1. That on hydrogen ion is +8. That's on iron 2 ion. As you can see, because of the 5, it's actually affect the charge and change it to +10. Now that on the manganese 2 ion is actually +2, and that of the iron 3 ion is actually +15. Now, if we want to do the maths, we find out that +2 + 15 will give us +17, -1 + 8 + 10 will also give us +17. So the sum of charges on both sides is actually +17. We've ended up balancing the charges on both sides. So that's just how we actually do it. And then at the end of the day, we just end up with a full equation. Before I go over to the next question, at the end of the day, this is our full equation. So let me just show you the full equation one more time. Now, this is our full equation. This is our balanced redox equation, and we've ended up balancing the charges and balancing the stoichiometric coefficient in front of all of the ions present. Now, let's look at an example. Now, balance the equation below under acidic conditions. Now, this is oxalic acid and this is manganese ion to actually give us carbon 4 oxide and manganese 2 ion. So it's still quite similar to the other one, but not quite similar. Now, the oxidation number of manganese in this is +7 and this in +2. So manganese is undergoing reduction, and hence manganese is the oxidizing agent. Remember, the first step is to identify our oxidizing agent and our reducing agent, so we can actually get our reduction half equation and oxidation half equation. So our reduction half equation, let me just call this red half equation, that's EQT. So our reduction half equation, if you want to write it down, it's actually going to be MnO4 minus is actually going to be giving us Mn2 plus. So this is actually a reduction half equation. So now the next thing is actually to identify our oxidation half equation. So let me just kind of like take this and write it again, so it actually be smaller, so we can do this on one page. So our reduction half equation is actually going to be MnO4 minus to actually give us Mn2 plus. An oxidation half equation should be the reverse of that. So our oxidation half equation, that's oxy, should actually be H2C2. This is C2O4. That's from the oxalic acid to actually give us 2 moles of carbon 4 oxide, because this is what they gave us in the question. So now the next thing we actually have to do is actually now to actually balance stoichiometric coefficients, like in front of all of these ions. Now let's look at the oxidation half equation. We don't really need to balance any stoichiometric coefficient because manganese and manganese remains the same. Now let's look at the oxidation half. Now they've already balanced the equation for us, like carbon is 2 here and carbon is also 2, so we don't really need to be balancing that. Also, oxygen also they balance it to be 4 and 4, but hydrogen will end up balancing that later on. So let's just go with the reduction half equation. Let's start with that. So the reduction half equation, I'll call this red. So now the reduction half equation was given to us as MnO4 minus to actually give us, so there is a 4 to actually give us Mn2 plus. So if we're balancing this under the acidic conditions, we must first of all add water to actually, hydrogen ion to the left hand side and water to the right hand side. So on doing that, we end up with this MnO4. Since we balanced this before, I'm not going to focus on this. I'm just going to write the full equation. Plus 8H plus should actually give us Mn2 plus this Mn2 plus 4H2O. So we'll actually be focusing on the balancing of the oxalic acid. So now this is what we have for our oxidation half equation. So let me just put it like this. Now for our reduction half equation, we end up with oxalic acid. Oxalic acid has H2C2O4 is actually giving us 2 moles of CO2. So these are oxy. So now let's balance this like in the acidic condition. So now let's look at it. Now we don't have any problem with oxygen and hydrogen, but we still try and balance that. So let's just end up balancing everything in total. Now we only have problem with hydrogen ion, so we don't really need to add water to the right hand side this time. All we just need to do is add hydrogen ion to the right hand side, because if we add water to the right hand side, we'll end up complicating the reaction, and balancing it again will just be a problem. So the simple way of balancing an equation like this is actually to add it's kind of like a reversible reaction. So the simple way of balancing this is always a reversible reaction. The simple way of balancing this is actually to add 2CO2, this is what we have, plus hydrogen ion, because we don't really need to add hydrogen ion to the right hand side, because if you just notice, the only thing that's actually giving us a problem is the hydrogen on the left hand side. So we just had hydrogen ion on the right hand side, and on balancing the hydrogen ion, we only add 2 here. So if you look at this equation, you find out that it's balanced already. So now this is our balanced reduction half equation. So now we have our balanced oxidation half equation, that is this, and our balanced reduction half equation, that is this. So now what's the next thing we actually need to do? Balance the charges also. So now for our oxidation half equation, let's try and balance the charges. So we have MnO4 to MnO4 minus plus 8H plus is actually giving us, this is reversible, actually giving us Mn2 plus 4H2O. So let's try and balance the charges. Now, total charge, we balanced charge before, so we weren't really going to be focusing on balancing charges. This the manganese reaction is not really like our major like focus. It's actually the second one, because this is just balanced in a way. So we balanced this before in our earlier equation, so we just end up with this MnO4 minus plus 8H plus 5 electrons will end up giving us a reversible reaction of Mn2 plus 4H2O. So this is what we have for our our reduction half equation. Now for oxidation half equation, the only charge that we actually need to balance now in this case is what? That is the hydrogen ion coming in place. So let's balance the hydrogen ion. So that was H2C2O4, a reversible reaction, actually giving us 2CO2 plus 2H plus. Now, in order to balance this, we actually have to add electrons to the right hand side. If you can still remember what I said, oxidation, add electrons to the right hand side. So we add electrons to the right hand side. Since the charge here, or the resultant charge here, is 0, this is a stable atom, this is 0, and this is plus 2. So what do we add? How many electrons do we add to actually cancel out this plus 2? We end up adding 2, so we end up having plus 2 minus 2, and that will end up giving us a resultant charge of 0. So we've ended up balancing our reduction half and our oxidation half. Now these are balanced reduction half, and the other is our balanced oxidation half. So the next thing we actually do is actually to multiply this equation by the stoichiometric coefficient of the previous one, and do the same for the reverse. So the stoichiometric coefficient of this previous equation, as you can see, of the electron in the previous equation is plus 2. So multiply this equation by plus 2, we end up with 2 MnO4 minus plus 16H plus 10 electrons will end up giving us a reversible reaction of 2 Mn2 plus 8H2O. This is the balanced equation. So let me just remove that emphasis I've made on the previous one. So now we've removed the emphasis made on the previous one. Now this is what we'll actually be emphasizing on now, because it's the equation that we have now finally. So now let's look at the other equation, like that's the oxidation half equation. Since this is our balanced equation, now let's also balance multiply that by 5, because 5 is the stoichiometric coefficient of that electron. So end up with 5 oxalic acid, that's 5H2O, 5H2C2O4, I'm sorry, end up giving us, this is reversible, will end up giving us 10 CO2 plus 10 hydrogen ion plus 10 electron. So if you can see from the previous equation, 10 electron, 10 electron. So what is just needed for us to do is actually to combine these two equations to form a whole resultant equation, and we'll actually be cancelling some other things involved. So now let's go. Now the oxidation half equation, that is this equation over here. We're just going to write it over there again. So we end up with 2MnO4 minus plus 16H plus 10 electron to end up giving us I think 2MnO4 also, 2Mn2 plus 8H2. So these are reduction half, right? So our oxidation half, that is oxy, will also be this. So let me just transfer it over there. That's what we have, 5H2C2O4 plus I'm sorry, let me just try and picture it again. Okay, so these are reversible symbol, and that will give us 10 CO2 plus 10 H plus and plus 10 electrons. Confirmation. Yes, that's the same thing. So what we actually now have to do, this is 10. What we actually have to do is to cancel out our electrons. We cancel this electron, we cancel this electron. Now notice that we have hydrogen ion on two opposing sides. So we can actually cancel the hydrogen ions too. Now we're cancelling the hydrogen ion on the right hand side. We end up with 0, and we end up with a resultant hydrogen ion of 6 here. Because it's just like minusing each other. Minusing the two equations. Now if you notice, like if you notice, the hydrogen ion 16 minus 10 will end up giving us 6. So we have 6 hydrogen ions present there. So what we do now is to combine the two equations. So this might take a lot of space. So let me just like separate these two. And now you cancel the two equations for these two. So let's combine two equations. That's 2MnO4 minus plus 5H2C2O4 plus 6 hydrogen ions will end up giving us, I'll just take this to this side. So let me just try and set a boundary. Okay, there's a boundary. We'll end up giving us Mn2 plus, that's 2Mn2 plus 10 CO2 plus 8H2O. So now these are the two combined equations that we end up having. So now if you want to actually calculate stoichiometric coefficients of all of the ions, manganese is 2, manganese is 2, if you're with me. Oxygen in the manganese ion is plus 8, it's 8. So an oxygen in the oxalic acid is 20, so we have a resultant oxygen of 28. Now oxygen in water, that is 8, and oxygen in carbon dioxide is 20. So the oxygen is also balanced to be 20. So now look at which other ion now the next ion, carbon in manganese ion, oxalic acid. If you look at the carbon I'm talking about here, the carbon in oxalic acid is actually 10, and the carbon in carbon dioxide is also 10. So those three are balanced. And the last one is hydrogen. Hydrogen in the left hand side, from oxalic acid we have 10 hydrogens plus 6 hydrogens. That's a total of 16 hydrogens on the left hand side. On the right hand side, hydrogen is only present in water, and that's also 16 hydrogens. You can also check to confirm if the charges are balanced. We have a resultant charge of minus 2 plus 6. That's, we have a resultant charge of minus 2 plus 6 on the right hand side, on the left hand side, and on the right hand side we have a resultant charge of plus 4 also. Let me just break this down, of plus 4. Minus 2 plus 6 is also going to give us plus 4. So we have a resultant charge of plus 4 on the left hand side and a resultant charge of plus 4 on the right hand side. So this equation also is balanced. So now, as this is meant to be acidic. So that's acidic. So now you can try and pause the video and attempt this, because I'm just going to be doing it. Just try and pause the video and attempt it. Let's see how good you can go. So now let me just start with what we have here. We break this down into the oxidation and the reduction half. First of all, by identifying oxidizing and reducing agents. So now the oxidation number of bromine in hydrogen bromide is -1, and in bromine, that's bromine liquid, is actually 0. So in bromine liquid it's actually 0, in hydrogen bromide is -1. So from -1 to 0, the change in oxidation number is actually that's an increase in oxidation number. So at the end of the day, bromine is said to be undergoing oxidation and should be a reducing agent. We can confirm with the sulfate ion. Now the sulfate ion actually has, like in sulfate, sulfur has an oxidation number of +6, and it changed from +6 to 0, and that's a decrease in oxidation number. So that's reduction occurring there. So oxidation reduction. So our oxidizing agent in this case should be our hydrogen bromide, and our reducing agent in this case should be our sulfate ion. So now let's break this down to the oxidation and the reduction half equation. So now the oxidation half equation, or let's start with the reduction half equation, that is from hydrogen bromide. So that's HBr. HBr is actually changing, or is actually changing to Br2, and our oxidation half equation, so let's call this our red, and our oxidation half equation, oxy, should actually be SO4 2 minus actually changes to SO2, actually changing, actually reversible reaction, so reverse symbol, actually changing to SO2. So that's our oxidation half equation. These are reduction half equation and oxidation half equation. Now we have our two equations. Now we can decide. Now let's balance the stoichiometric coefficients on their own. Now for hydrogen bromide, there are two bromine atoms present here, so we have to add two to actually balance the bromide atoms present there. Now also for the oxidation half equation, sulfur is actually balanced, so we don't really need to balance it. It's only the only thing that's left unbalanced is actually the oxygen, and we'll actually balance that later on. So now on doing this, the next step is actually now to balance them in their basic medium. That's either acidic or basic medium. Acidic medium, since we're dealing with acidic medium. Now for the reduction half equation, we should end up with this HBr. So red first, this is red. So HBr is actually a reverse. So the reversible reaction, these two HBr should be giving us bromine liquid. So now this bromine liquid, now for the reduction half equation, now this bromine liquid, so what do we add, if you can remember, we add hydrogen to the right hand side. We don't really need to add water in this case because there's no oxygen present, so we just add hydrogen to the right hand side. That's hydrogen ion, and you add two hydrogen ions if you've actually been trained by yourself. Add two hydrogen ions because there are two hydrogens present in bromine. So now for the oxidation half equation, so we call that oxy, so that is SO4 2 minus the reversible sign. It's actually changing to SO2. So let me just give a little bit space so we can, because we're actually going to balance in this in a more in a better way than we actually balance the previous one. So we end up having this, and this is SO2. So we add water to the side, that's the we add water to the right hand side, and we add hydrogen to the left hand side, just like we normally do. The reason why we didn't do it for a previous one is just because we didn't have any like oxygen atoms, so we just need to balance the hydrogen ion, and on balancing that's why you don't really need to abide by the rule. You can just use your mathematical sense and just actually break it down by yourself. So the rule is not really something we really need to abide by. Just have to understand the procedures or what's actually happening. That's the best way to understand this. So now the next thing that we actually have to do is add water here. That's H2O. And how many, like, if you can see that difference between the oxygen atoms in the two atoms, actually this is 4 oxygen atoms, and on the right hand side is actually 2 oxygen atoms. So we have to add 2 to actually balance the oxygen atoms, and on doing that we also have to add 4 hydrogen ions, 4H plus. Now we've ended up balancing the left hand side equation and the right hand side equation. Now the next thing we actually have to do is to balance the charges. Let me just balance the charges on the same page. So the resultant charge here is actually 0, and that here is actually +2. So we just need to add 2 electrons here to actually balance the charge there. So now on this other one, now the resultant charge here is -2 plus 4. So this +4, -2 plus 4 is actually going to give us +2, and down the right hand side it's actually 0. So what I actually have to do is add 2 electrons to this side, so I'll just put it in front here, 2e minus. Now, if you can look at it, or if you can look at the two equations, we added two electrons to the reduction half equation, added two electrons to the oxidation half equation. We don't really need to multiply them by anything because the electrons are kind of balanced by themselves. So we just need to combine the two equations without multiplying anything. So that's the next thing I actually need to do, combine the two equations. So let's combine the two equations. So now the reduction half equation, the oxidation half equation, that's HBr, 2HBr plus I'll just going back to actually see what I'm actually doing because sometimes I just actually slip off from my mind. So let's just go back. SO4 2 minus plus 2H. So this SO4 2 minus plus 4H plus with 2 electrons plus 2E minus is actually going to be giving us, so let me just take it like this. It's actually going to be giving us SO2, that is bromide Br2 plus, bromide liquid plus SO2 plus that is 2 hydrogen ions and 2 water molecules, 2H plus 2H2O plus 2 electrons also. So we can cancel out the electrons now. We cancel out the 2 electrons. Now we cancel out the 2 electrons. If you also look at what we have here, we can also cancel out hydrogen ions because they're on 2 opposing sides. So on cancelling out the hydrogen ions, we end up with a resultant hydrogen ion of 2H plus on this side and 0 hydrogen ions present on that side. We can't actually cancel any other thing. So what we actually need to do is actually to combine the two equations and just, so let's combine the two equations. So we're going to be combining the two equations now. That's actually 2HBr plus SO4 2 minus should give us okay, let's show something, plus 2H plus should end up giving us Br2 minus, Br2, that's bromine liquid, plus SO2 that's sulfur oxide, and plus water, that's plus 2H2. So this is the left-hand equation and this is the right-hand equation. So you can actually check if molecules actually balance. Now let's start with bromine. Bromine, 2 on the left-hand side from hydrogen bromide and 2 from bromine liquid also. Let's go over to sulfur. Sulfur, 1 on the left-hand side from sulfate ion and 1 from the right-hand side from sulfur oxide. Now the next ion that will actually bounce in is oxygen now. Now there are 4 oxygen from sulfate ion, 4 oxygen here. Now the oxygen present here, there are 2 from the sulfur oxide and there are also 2 from the water. That's making a total of 4 on the right hand side. So we have 4 on the left hand side and 4 on the right hand side. Now the last ion that will actually be balancing, or the last molecule we're actually balancing, is hydrogen. Now there are 2 hydrogen on the left hand, 2 from hydrogen bromide and also 2 from hydrogen ion. And on the right hand side also we can actually see 4 from water molecule. So now this last example, I would like you to try and attempt it yourself. Just try and attempt it to see how good you've gotten in oxidation reduction reaction. So that's just where we'll be stopping for today. So that's what we'll just be stopping for today. So just thank you for watching. Have a lovely day. I'm not going to be doing tutorial example. I want you to actually try and attempt it yourself. So the next time next video we're actually making is talking about balancing redox reactions under the basic conditions, since we've all seen how to balance redox reactions under the acidic conditions. So thank you.